Okay, good morning. So this is week number 6. We are going to discuss clustering algorithms. So over the last 5 weeks, we gone through the fundamentals for linear algebra. So for the rest of the lectures, we will focus on more application. So utilizing the foundation you have just built. So we get the idea of vectors, matrix, multiplications between matrices, dimensionality reduction, the distribution, those histograms, how to compute distance. So let's have a quick review for what we had. So this is a website for the course. So in week 1, we have this history of machine learning. We talked about the language, the computer languages. Have a quick introduction of what a single cell technology, especially 10x genomics, droplet-based. In week 2, we had this introduction of the multiplication of matrices and vectors. We mentioned eigenvalue, eigenvectors, and introduced the idea of using squared matrix as a rotation matrix. In week 3, we talked about the similarities and distance between data points. There you learned multi-dimensional scaling. Okay, remember, if you have pairwise distance between cities, between data points, you can reconstruct a map to put those points in the 2D space, let them to satisfy these distance matrices. So this is all introduced here. In week 4, we discussed about the probabilities, distributions, generative modeling. Remember, I try to simulate the height of people in Italy and Sweden to give you the idea how you generate those distributions, if you know what distributions you are talking about. But it's very difficult for single cell data. So last week, we talked about dimensionality reduction. Your homework is to explain PCA. I said PCA, if you know how to explain, you need a lot of knowledge in linear algebra in order to explain that very clearly. So you have to maybe cover all of this previous knowledge from the previous week. That is also said PCA, if you can explain that very clearly in your homework, for example, you understand about half about this machine learning, because the rest of them, for example, today, clustering, we will utilize distance, we will find a way, for example, rotate matrix, the data points before doing this. So a lot of technique in there related to what the PCA has already gave to you, the concept at least. And T-SNE UMAP are the most commonly used dimensionality reduction technique we are using in our single cell data processing almost every time. But that's a relatively new technique, and it's based on the generative modeling. So your probability and the distribution idea contribute for your understanding of the T-SNE UMAP. So today we are going to talk about this clustering algorithms. I will go through k-means, DB-scan, spectrum clustering, and SC3. This is a algorithm which is developed for single cell data specifically, okay? And then there are hierarchy algorithm also for clustering purpose, but not commonly used. Okay, we mentioned in the first class, this is a supervised, unsupervised learning. The example I gave for supervised learning is regression and classification. Well, the clustering algorithm, the procedures we are going to discuss today belong to unsupervised learning. That means you only gave your the input data, for example, your matrix of gene expression in different cells. So this algorithm is unsupervised. It does not require any extra information. So unlike regression classification, you need to give the training data. You need to tell the algorithm input matrix and cluster membership ID for the cells or genes you are going to classify into. But the clustering algorithm will not require this classification information. It only helps you to group your data points into clusters. So this is used for automatically organize your data, understanding the hidden structure in your data. See whether you have multiple small clusters or you just have two bigger ones, or there's no cluster, then you only have one major cluster. So this helps you to understand the structure. Then for the pre-processing, for the future analysis. So after your dimensionality reduction, then you start to cluster cells into groups. Then you move to next step. So what our next step is? In single cell study, our next step will be annotate the cell, the cluster of cells. So this is a workflow, and you have already seen. You understand from a matrix to this t-SNE or PCA dimensionality reduction figure. Okay, so we can start from here and then apply clustering algorithm to group those cells into different clusters. Then your cell type annotation will based on the cluster you just made. So you are going to assign a single annotation, a single name of a cell type to this cluster, to this cluster, to this purple cluster, to this blue cluster. So it's important to have a good classification, clustering, so make sense to you, because you are going to do next step will be group based rather than individual cell based. Okay, so you group them together and look at as a group to look for the marker genes. And then, so if you look at this, each, so this is a violin plot. Each violin is a group of a cell rather than a single cell. So you assign labels to a group. So that's very important to have a good clustering algorithm to help you group the cells into clusters. Well, it looks like a very easy task sometimes for human. This is an example we had before, and this is a t-SNE plot. And from our understanding, the majority of cells should be astrocytes, and there's some unknown, the microglia. If you gave this to clustering algorithm, for instance, if you give this directly to k-means, k-means is most commonly used. Okay, so if I say, I want to cluster this data into 3 clusters. Well, the k-means algorithm will give you the solution looks like this. Okay, there's one cluster here, and there are blue cluster here, and the teal cluster here. all if you run multiple times, you always get some kind of solution like this. But if you are a human being and you may select, you may drag your mouse and say, okay, this is a major cluster here. This is another one. This is another one. So this really makes sense to us, but for some of the algorithms, if you don't select wisely, you will have wrong clustering results. So why it's hard? Because the density, the relative distance between cells change greatly between this cluster and that cluster. So some of this algorithm will not be able to do very good job for clustering those cell representation of the low dimensionality representation, because of the density of the cells in the cluster changed drastically. Okay, so you need to wisely choose why you should use, for example, spectrum clustering rather than k-means in this case to do things. So that's the algorithm I have to explain to you, so you know what to do when you have real data. So the major clustering algorithm approach can be classified into partitioning and hierarchical, and the model-based, and the density-based, and the graph theory. So we are going to focus on partitioning algorithm most. We'll mention this model-based, density-based, we will use dbScan. Graph-based, that will be spectrum clustering. At the end, because this is hierarchy based, it's not commonly used, I will leave to the end. So they all are general purpose clustering algorithms, not only designed for single cell data. And as I mentioned, they're SC3, which is originally designed for single cell data clustering. So k-means is partitioning method. Gaussian mixture modeling models is model-based. dbScan is density-based. Their density cluster is an extension of dbScan. It's also density-based. Their affinity propagation. So their reference, if you are interested in this, is graph-based. And we will mention the spectrum clustering. Also, you trade the cells. You first build a KNN network and make a graph, then work on this graph to cluster cells into clustering. Basically, you are detecting models, subclusters in the network, subnetworks in the big network. I want to mention, so once you know how this works, and in computer session we will play a video later. So this is a real application in clonal sites annotation from our another lab meeting. And we have a discussion and utilizing clustering first to cluster cells, and then how the annotation will be done up on the results of application of this clustering results. So something like this. So we will watch this in computer session, okay, Thursday. This annotation, you see this clustering of the cells into many, many small clusters. So this is utilizing k-means algorithm. Then we annotate each subclusters individually. The strategy we use is if they have the same name. So for example, 13, 18, if they share the same cell type name at the end, the two clusters will be merged into just one. Unless you really want to identify the CD8 plus T cells, you can have those marker labels rather than a whole T cell clusters. You can have subclusters to name them differently. But that's a strategy we are going to use in the toolbox to understand. So k-means is the most important general purpose partitioning based clustering algorithm. So this is mathematical description of k-means cluster. So it is a grouping of a subset, a set of objects or data points. So that object in the same group. So the final goal is you set up this membership. So in the same group of those members, those data points, they are supposed to be more similar to each other compared to other data points which not belongs to this member. So you need to have an algorithm to automatically. So this automatically identify hidden structure in the something like this. Okay, you identify potential memberships. So you consider this as one member, this as another. Third. Okay. At the very beginning, we have this observation x1, x2. This all x1, x2, 3, every member, xn. Okay, every observation. Now we need a so-called hyperparameter. Okay, we need a hyperparameter. We need hyperparameter k. So k indicates how many clusters we want to obtain from the observation in data. So you have so many, you have n data points, and in your imagination first, okay, how many clusters you want to give. This is integer, so in our case, it's 3. I'm going to make 3 clusters. So if you gave 2, so I set my hyperparameter into 2, I may have a solution which will be different from this. I will have a solution. This is 1 and this 2. Okay, when you have it. So this is only parameter, the number of clusters k you have to give to the k-means algorithm. So at the end, what you achieve is this groups. This groups is, for example, we gave this 3 as an example. Okay, 3. You will achieve something like this. You will achieve, because k has 3, so you have a 3 center point. So let's see 1. Let's see this C2. This C3. What you will achieve is the distance. You know how to compute the distance between points. Especially, and by the way, we still can consider this as a vector. So each point is a vector. How to compute the distance? Distance is your vector x, the I, minus the center. So we have a k, so let's say k1, k. So that I belong to. So because this point belongs to this center, so we have this will find the distance between each point to its own center. So when we compute the distance between data points, we use vector difference. Then we have this two vertical bars in the norm, okay? The magnitude, basically the magnitude of this difference. So that's the expression between each data point to its own membership center. And you for the squares, basically you have a squared distance. It doesn't matter you have this or not. What you want to have is the total of this is small. So you minimize this. What that means is, let me use green lines to indicate what this is. So this is from xi, x1 to center C1 itself. x2, which center C1. So all this distance, and this to itself. Here about distance, this to that. Okay. All the data points to its center of the member it belongs to, and everything add together. So not only this group, but also C1 group distance, or the data points to the center. C2 members to its center. C3 to its center. Everything add together. You have this. When this number at the end is a single number, when this number is small, the smallest, you have the solution. You found the three centers, and you found the members of each data point belongs to. If you make the mistake, for example, you say, okay, this x2 I will assign into the C3 group. Okay, what will happen? You have to compute the distance between your x2 data points, because you assign x2 into the number 3 cluster center. So you need to compute x2 to the C3 center. So this distance is large. You will, if you have a misassignment, you will have an increased distance. Your total will be higher. In that sense, you have not achieved for the final classification group of your member for each cluster. You have not achieved the minimized solution yet. So you have to change the membership. Okay? So the next slide will explain to you and how this search for the 3 center, as you have k equals 3, so you will find the 3 center. How these 3 centers will be located. If you put the C3 here, and in the middle of these two, you may not have a good solution at the end. So you need to move centers as well. So how you adjust the center of your K, of your clusters, and also the membership assignment for each point under your consideration, and which center it belongs to. So that's the solution you have to work out computationally. So the procedure will be something like that. So this algorithm have a history, and 1957 had been published in that year, the idea. So we just randomly put 3 centers assume we have no idea whatsoever, so we start from this, something like that. That's our data. That's our data. So we just start by randomly put three centers. So we take C1 here, C2 here, C3 here. So you know your data is from the smallest to largest. You have a range. Okay, you know where they're located in 2D, 3D, or even higher dimensional space. So in that given space, you put three random centers. Then you start to compute. You start from the distance between your data points. So, for example, let's start from this data point. So this is example xi. My first step will be compute the distance between xi to c1 to c3. I will compute three distance. Distance is very easy to compute. It's just vector, one vector minus another, and take a norm. Right? It's very quick. I can compute the second to all of them. If it's close to C3, I will assign temporarily xi belong to this because they are close to each other. Closed center, and move that to there, belong to that. I will do the same thing, and then the first round of assignment happens. Okay, by randomly, and this is close to those data points. All belongs to that. So after the first round, let's see. Let's make after the first round. So this C3, and I will include all this. C1 will include all those data points. See. Okay, so this is very easy, right? You assign them first. After that, I will compute based on assignment. So now I have those data, this data belongs to C1. I will use current data belongs to this cluster to recompute the center. So right now, C1 is here, and those belongs to C1, but the center is some kind of tilted off the center. Actually, if I look at this point, the center should be here, right? So I'm going to move this original center to here, because depends on the member belongs to center. The center is supposed to be in the middle of this. Majority of the class points belongs to them. I also have to move C2 to here because looks like all this member belongs to C2 should be centered here. And I have to move C3 back to somewhere because most of this first round assignment of the members should be centered here. So I move my center around. So I finish the first round of this center movement, center node. Then I start again as a refresh, because at the beginning I have a 3 random center assigned, but now it's somehow justified in the center by the data themselves. So I start from beginning again, so I will compute each point's member, recompute the members according to this new center arrangement. I will say, okay, this is center C3, and C2, I change. So after this round, I will reconstruct the center, and from the data points have been assigned to this center, I will move my C2 accordingly. C3, I move my center around. I finish the second loop. And then I'm going to do the iteration again for the third round. Okay? So I will do as a fresh and start to assign data points to the center, see which one close to the center, and assign to them. And do that again. So after several round iteration, my center position will be fixed. Then I detect there's no change from the previous step of center location compared to next step. So I stop. Then that's the solution for the k-means algorithm. I stopped the center location, 3 centers, because I have a hyperparameter equals to 3, and I finish. So once the center location is fixed, all the members belongs to that center will be the solution for the cluster membership. Okay, so all the points close to C3 will belong to cluster 3. All the points which nearest to the center C1 will belong to cluster 1 and 2 the fixed. Okay, so that's the procedure. And this is a mathematical description of objective function. So SEK, so this is a single number. This single number contains 3 numbers. In our case, because it's case 3, then you have a big K1, big K2, big K3. So we need to have 3 numbers. The summation is minimized. So within each member, there's a distance to the center. This value has to be smallest. So you minimize this value, and the 3 of this minimized value, the total will be the smallest. So that's, we want to achieve the smallest value for this objective function. So this is like a optimization problem. The solution for this optimization problem is to first, as I said, randomly assign this centroid center, and then assign membership, and then move the center based on the members until you reach to the stage that there's no change in the location of this centroid. And then then the solution of will be the minimized, or the within the group distance summation is minimized. And each group is minimized, then the whole objective function is minimized value. Description, so determine K and initial the cluster centers randomly. Decide the class member of n object by assign them to the nearest class center. Re-estimate the center by assuming the membership found about is correct. You assume that's correct, then the center should be here. And you move your center and then do this, go back to step 3. So you have a loop here to repeat until convergence. Convergence means the center location, not a change, okay? It could be non-zero, but the difference very small. You have no you don't have to change anymore. So that's the solution at the end. This is supposed to be a cartoon, and just describe what I just described on the whiteboard here. They use two clusters, k equals 2, and they have a center assigned into red and these yellow triangles. And use the nearest neighbors. So you found those belongs to one red center, and those belong to yellow center. So assign the members. Then you use the members to compute the center by taking the average of their x, y axis coordinates values, and you move your center to here. So after move the center, then you recompute the membership, because this new center has been moved to here as a red center. So you have to reassign, and these two yellow data points belong to yellow now have been assigned into the red group because the new center has been given. And this red member now has been assigned into the yellow group. So after this round, there's no change, because when you compute the center, the new location of the red point are very close to this this previous steps. So there's no major changes, and you finalize the membership assignment. So in this small example, you only need to do one. You move 1, 2, just 2 steps. So iteration, just 2 loops. Very quickly, you get a converged solution. So in real data analysis, we found this is a highly k-means algorithm, highly efficient. And you probably don't need 5 loops to solve the membership assignment in many, many points. In this small example, you need 2 iterations. In larger ones, you may need 5 or even 10. Should be more than enough. So, and all the operations are distance computation. It's all just one vector minus another, and take norm. That's all the computation you have to do. So that's very computational efficient, so commonly used. Okay, we will very quickly mention this model-based Gaussian mixed model. In here, there are completely different strategy of the same things. So we had something like this, and we try to find close distance and membership. But when you talk about the Gaussian modeling, we consider those data points was drawn from a normal distributed distributions. So if you look at, for example, this one, let me clean it. If we still have some data, something looks like this. So the modeling we will consider, for example, by the x-axis, and we will consider this was generated by 3 normal distribution data. Okay. All right. So if you sample the x values and utilizing this small normal distribution, then you can construct those data points here And also you consider y, and you consider, okay, this is one, this is another. Okay, so you can do this in 2D, and just utilizing normal distribution to try to put them, try to fit this data into, say, several parameters here. So you have mean, standard deviation, you can reconstruct those. So that's the idea. So you utilize this distribution to assign the membership. If you believe you need 3 normal distribution to capture the variability in this, or sometimes you need to say, okay, I only need 2, so you don't have to assign 3 groups, and you use the distributions to assign the membership of those data points. For example, those are the blue members, and those are the yellow ones. So this is kind of a model-based, distribution-based, fit your data points and just assign the membership. So this is one way. We just very quickly to mention that. So in the many options of the clustering algorithm, you can, once you know, okay, this is a mixed Gaussian model-based algorithms, you know what's going on, and within the algorithm, this algorithm called EM algorithm, expectation and the maximization, is also its iteration, and their expectation and maximization are 2 different steps, so you can do this fitting very quickly. Okay. So this is kind of a shortcut of this optimization procedure by giving you have this well-known distribution, so you can use this technique, iteration-based technique, very quickly to get a solution. However, there are limitations, as I described previously, and if you had the major density change, you only be able to use k-means cluster to get the ideal clustering results. Just like what I just drew. If you have this cluster, well, this cluster is so k-means get confused, see whether a center should be here, so then you have this center, this center. It's not going to give you this more intuitive solution, something like that. So this is one weakness. The density, okay, major change of density of the clusters gave you some problem. And most importantly, you cannot do this so-called non-convex shape. So this is a convex shape, but it also belongs to non-convex shape. K-means will not work very well for this if you have data points. So this is a density difference if you have data points which is a half-moon shape, or this shape. The k-means will definitely give you one cluster here and another cluster here. So this shape, the distribution of data points will create some difficulty for k-means algorithm. So this is an illustration of that problem I just talked about. So k-means gave you a solution if this is real membership, blue points, red points. K-means is okay in this case, we found 2 centers. Well, if this is a real membership, red and blue points, and the k-means will find the center here and give all these points belong to red, and this belongs to blue. So this shape is non-convex shape of the distribution of the points. give you difficult. It's harder. The k-means definitely will not follow this, and they will give you this one cluster, this another, this will be another. When your data also have the mixture of non-convex and the convex shape, k-means will not give good solution for this. Okay. So any questions so far for the k-means? Because we are going to use k-means all the time in real data. Okay, so in order to solve this density problem, you know, develop this so-called DB scan algorithm, this density-based spatial clustering of application with noise, so DB scan. It's a paper published in 1996 described this algorithm. There are a lot of reference about it. So the idea of this is to create this circle, and then you move your circle along with, so basically you create a lot of small circles, okay? Move along with this membership boundary and all this kind of concepts. But it's quite intuitively sound, so it's very easy to understand if you read through this procedure. I will have a play a video rather than I just explain this. So they have the idea of two parameters, okay? So you need to design the radius of the neighborhood. So you start to have design this small radius of so-called neighborhood. So you can have a lot of neighborhood if you have a small radius. Then you need another hyperparameter. Remember, hyperparameter k-means is only one number, but for the DB scale you need two, and this is a radius, and also this m, so minimum numbers of points inside these neighbors. So you need to have for example, at least 3 numbers in this neighborhood in order to be treated differently, okay? So if you don't have this minimum number of neighbor members in this small neighbor, you will be treated differently. So that's 2 hyperparameters for the DB scan. And you move, and so you join those neighborhood, small neighborhood. If you satisfy certain criteria based on the radius and the minimum number of the members, you start to get rid of those unlinked neighbors. So make a small neighborhood, become a larger community based on those selections, based on your criteria described by these 2 parameters. And then they will be connected at the end. So those will be connected based on the conditions you set up. If they're same communities, the neighborhood will be merged. So there, I put some this DB scan explanations, 2 of them. So I'm going to just play one and before the break, okay? So this is a shorter version, but it's intuitively so, okay? To let YouTube to explain this.
When I'm sketching out a new
Sorry about that.
feature, There's just so many unknowns, and Codex really helps with that. It helps me understand external dependencies on whatever else the team might be working on, so I can hit the ground running.
Hello! In this video, we'll be covering density-based clustering. Density-based clustering is also known as dbScan or density-based spatial clustering of applications with noise. It works by defining a cluster as the maximal set of density-connected points. There are two parameters that are taken into account, epsilon and minimum points. Epsilon is the maximum radius of the neighborhood, and minimum points is the minimum number of points in the epsilon neighborhood to define a cluster. There are three classifications of points. They are core, border, and outlier. A core point has at least minimum points within its epsilon neighborhood, including itself. These are points that are at the interior of a cluster. A border point has less than minimum points within its epsilon neighborhood, but can be reached by the cluster. That is, it's in the neighborhood of a core point. And finally, an outlier, or noise point, is a point that cannot be reached by a cluster. A point y is said to be reachable from x if there is a path p1 to pn with p1 equals x and pn equals y, where each pi plus 1 on the path must be core points, with the possible exception of pn. An object y is directly density reachable from object x if x is a core object and y is in x's epsilon neighborhood. A is directly density reachable from B, B is directly density reachable from C, A is indirectly density reachable from D, D is not density reachable from A, since A is not a core point. Density-based clustering works by picking a random point that does not belong to a cluster or is an outlier and determines if that point is a core point. If not, label it as an outlier. Now we'll pick another core point at random and determine if it is a core point. If it is a core point, then all of the directly reachable nodes are assigned to the cluster. Then do neighbor jumps to all reachable points and add them to the cluster. Keep finding neighbors until you're unable to. This point would be labeled as a border. Now keep repeating steps 1 and 2 until all points have been labeled or assigned to a cluster. In this case, the last 2 points are also outliers. Now we have our cluster. At this point, it's important to know the difference between density-based clustering, or dbScan, and k-means. dbScan is effective at cutting the noise out of datasets by labeling them as outlier, whereas k-means uses the entire dataset. In this example, we have 2 sets of clusters resembling half-moons, each belonging to different cluster sets. Now if we add some noise, we can see if dbScan or k-means correctly assigns the clusters. Let's run dbScan. We'll see that it'll correctly group the top half-moon as a cluster, and it'll do the same for the bottom half-moon. Then it'll predict the rest of the points are outlier or noise, which is correct, of course. Now, let's look at the same half-moon example using k-means. This will also include the noise data points. Now, 2 random centroids start off, and the collective points are assigned. Then, each centroid is moved accordingly to their new locations. And once again, the collective points are assigned. And this cycle repeats until the centroids are at the point where no new points are assigned to either side from their movement. Once k-means is complete, we can see that it did not correctly predict the half-moon clusters, nor the noise. K-means has a huge disadvantage in that it considers the whole dataset and cannot distinguish noise from cluster groupings. It might also identify clusters incorrectly due to its reliance on centroid placements. Thanks for watching.
For a 5 minutes break. Then we come back to see the limitation for a DB scan. Okay. Yeah.
I'm very sorry for making it this late. I was very busy in the lab and
Yeah.
we were trying to leave. It was getting very late.
Yeah,
I
no
didn't see
problem.
the time. I'm very sorry.
That's fine. Okay, so the biggest problem for the DB scan algorithm is the result is sensitive to the setting of the parameters. So we have two parameters. We can select large radius or smaller minimum numbers of points, or we can smaller or anyway. Any combinations will give you a slightly different results. That's a bigger problem. So we don't want to have unstable results. So sometimes you get this particular cell belongs to this cluster, not that one, but when you change the radius, and the membership assignment change. So that's definitely something we really hate about it. So in real application, I don't see DB scan have any values, and we are not going to use it, and nobody knows how to set up its parameters to get the so-called optimized solution. There's no optimized solution. Later on, and I believe this is year 2014, another publication, try to improve some of those to find the density peaks and then have some pre-processing of the data before run the DB scan. So this is using a so-called decision graph, basically try to find outliers and try to improve, but still have a very limited modifications. So we are not going to talk too much. If you are interested in how this has been done and how you use this decision graph, so-called decision graph, you can name it by yourself. You should create a new algorithm to determine those centers, basically, class centers. So you see, using this decision graph with these two parameters they defined, you can find 1 as one center, 10 as another center. At the end, you will have 10 as your center and y as your center to assign this. So I'm going to move to graph-based, okay? No density. So we will be building a network, basically. So if you have data points, we are going to compute the pairwise distance. So you have d, I, j, okay? So that's the distance between each pairs. So not only compute their neighbors, but also you have a distance compute from this point to that point. Everything, okay, fully connected. This matrix, we discussed this distance matrix in one of the lectures. I don't remember the week 3 or 4. So it's about the distance between all of them. So dij will be one of the member in this. So you have a point I to the j. Then the value here is the distance between two data points. And this is symmetric because dij equal to dji. So you have I should be. So these two values should be the same. And the distance between the point itself should be 0. So you should have something looks like this. And you know how to compute this because you know how to compute the distance between points by one vector minus another taken norm. Okay? So this pairwise distance is the foundation for us to build network. So we are going to set a cutoff. See, we need minimize d need to be smaller than a number. So you have some distance, you have a number. So say okay, you need to have a cutoff in order to see, okay, I need at least distance to be smaller than this, I will keep it. So you go through this filter and to remove from this distance matrix, remove large numbers. At the end we will get some kind of filtered distance matrix. This 0 is all here. And if this value is too big, I will be removing and reset into 0. So I will have a lot of zeros, but at their place, which we still have values. So this is filter distance filter. So this convert this distance matrix into a so-called adjacency matrix, ADJ. So this is a network. So on the on this graph here, that means I will remove the link between this point to this because it's too long. I only keep certain distance which keep those links, have a distance smaller than a given value. Okay, so the link between this to that, it was there, but because the value is too big, I cut it off. It was here, and the filter will remove it. So you have a filtered version of this distance matrix, and you can use this as an adjacency matrix, which to represent a network or graph. Okay, so computationally or mathematically, this same graph or network is the same. So it's just like that. Okay. So let me call this A because it is an adjacency matrix. So all the downstream analysis is with this A. Okay, so we are going to use linear algebra for A. So all the downstream will be playing with A to do some things. To do things like you can treat this as a data matrix. Okay. You know it's a matrix. It's a squared matrix, and with some zeros in there, but you can still treat this as a data matrix. So we will apply some transformation, some decomposition, the eigen decomposition on it. In order to achieve something like this, we will, at the end, we will be able to detect those connected, densely connected neighborhood in this network. It's a sub-network, and you can call it modules. Okay, there are multiple modules. You detect those modules, and there are linkers which are between modules, like a bridge. Okay, so something like this. So you use this detection of network, sub-network modules as an approach to cluster data into group. So we have a data here. We build a network. Okay, this is called a KNN network. They call the nearest neighbor network. So the approach I just described. So you build this and do decompositions of a spectrum clustering algorithm. It will be applicable for all of these situations. So you can correctly assign clusters for this type of data. This will also work. This also work. So this is adjacency matrix representation of the network. Okay, so for example, this small network have 6 members. Then we need a 6 by 6 squared matrix to describe this. Okay, if 1 and 2 are linked, you put 1 here. 1, 2 linked, 2, 1 also linked. And the 3 and the 4 is linked, so 3 and the 4 is linked. Put 1 there. 2 and 4 is not linked, so there's no 2 to 4 value for this. Coordinates are 0. So this is a representation of the network. Same thing here. We have a cutoff, and we have 0 and non-zero values here. You can binarize it. Okay. Binarization to get this graph. It can be weighted. So this, if you don't put 0, 1, if you don't put 1 here, you can see, okay, this is a strongly connected between 4 and 6, and maybe 2 times or 2.5 times stronger than the rest of them. So you can have 4 to 6, this value put into 2.5, something like that, okay? So this can be a weighted matrix. So then we will have a so-called degree matrix. Degree matrix will be something look like this. There's all zeros, but only the diagonal position have a value. So those values indicate how many linkers each node has. So one have 3 linkers. One is connected with 2, 3, and 5. So you put 3 here. And the node 2 have 2 linkers. And then you put 2 here. So how can you compute the degree matrix? You can just sum the columns of your adjacency matrix. If you count, this is the first column of the adjacency matrix. The first node have 1, 2, 3 members. So you just put 3 in here. That's a degree for node 1. And this node 2 only have 2. and node 3 have 3, so we sum this column. So it's very easy to compute the degree matrix. So A, and then you can have, your A is your definition, then you need a D degree matrix. A, you can compute a D. So this is a degree matrix, not a distance matrix. Okay. Distance has already been taught. Now we are going to compute a Laplacian matrix. So this is called L. It's just a matrix subtraction. So you have degree matrix minus adjacent matrix. And you create something looks like this. In the diagonal position, there are positive values and indicate the degree for each node. And the rest of this could be negative or 0, depends on the difference between 0 to the adjacency matrix elements. So this create this is called a Laplacian matrix. This is a squared matrix. So all of them are squared matrix. If you have n nodes in your data, then you have an n by n matrix. If you are dealing with, say, 1 million data points, that will be a huge matrix, 1 million by 1 million. This is also 1 million by 1 million, and then the operation are the same, just a different dimension, not a dimension, different size, scale, depends on the number of your data you play with. Okay, so people figure out this Laplacian matrix is very useful. So L is information rich. It contains information of each element, each node, the connectivity value. It also contains information about how you connect it, which member, and how. So this is a mixture of multiple sources of information together. So the spectrum clustering or partitioning, this algorithm will based on Laplacian matrix decomposition. So let's see, this L matrix is a D, A. Then we will do the decomposition. Remember, for the square matrix, we can write square matrix, so L, then we can have its eigenvector matrix lambda 3. So that's vector, and that's the eigenvalue. If you look back to your previous slides, I can't remember which, maybe the second week. So we introduced something look like this. I remember I was given this using A, but now just replace this A with L. So Laplacian matrix. This is squared matrix, and then you can decompose. So once you compute this, okay, so you can use eigenfunctions, so eigenfunction. So give this L as input, you will get, remember, you can get V and lambda. That's output. That's in the MATLAB. So this is very matured algorithm and has been polished over the years. So eigen decomposition to give the squared matrix to compute eigenvector and eigenvalue. And we will need these eigenvectors. There are multiple eigenvectors you can find and put them together. So those are the eigenvalues, eigenvectors that you will find with the columns are eigenvectors. You will find multiple eigenvectors,